Hi, today I want to take a look at two tiny basics from Japan in the late 1970s.
Hey kids, it's the 6502 show.
The first language we're going to look at is Dendai Tiny Basic. It was conceived right here at Tokyo Denki University, a technical and engineering university that had been around since the 1920s. And it was the brainchild of this fellow, Mr. Yasuda Toshiaki. Dendai Tiny Basic was for the 6800 what Li Chen Wang's Palo Alto Tiny Basic was for the 8080. The interpreter was detailed in the appendix of this book. This is a Blueback's book called Use My Computer, Peripheral Devices and Actual Usage by Yasuda. It was published in 1978. The Blueback's books of science and technology were very well known in the 60s and 70s and into the 80s in Japan. So while Yasuda took some real inspiration from Palo Alto Tiny Basic and the Japanese version, which was the Tokyo University version, he had to develop something that was going to be just for the 6800. And so Dendai Tiny Basic was born. Let's take a look at it in comparison to two other much more well-known, at least in the West, Tiny Basics. Here's a basic comparison of the three languages we're going to look at. And the first two, if you're in the 6800 world at all, these are very familiar. TSC Micro Basic Plus and Pittman's 6800 Tiny Basic. It's the only one of the bunch that holds to Dennis Allison's original specification for the language that had an intermediate language as part of the interpreter. Well, you can see that by footprint, it's about the same size as Pittman's, Dendai that is. TSC Micro Basic Plus uses binary coded decimal for its numbering system. Another major difference is Micro Basic Plus has two-dimensional arrays. Dendai has a single array of a single dimension, and Tiny Basic doesn't have any, though that can of course be overcome. Maximum line length's about the same. You can have multiple statements on a line with Dendai and with Micro Basic Plus, and line numbers matter. You're not going to write a program that's got 10,000 lines of BASIC in it anyway, so don't worry about it. With the various commands and statements in the languages, here's where we have a big separation between Dendai Tiny Basic and the other two. There's just a lot more that Dendai does. With commands, Dendai adds an auto-numbering function. There is a cassette load function, and there is a print string, which essentially tells you how much free memory you have left. With Micro Basic Plus, you do get read data and restore, and for and next, and that is really cool. Dendai does pretty much the same thing, except you don't have the data structures. It can be overcome with rem statements, but it's a pain in the butt. And of course, Pittman's Tiny Basic doesn't have any of that stuff. When it comes to functions, Dendai again comes out a little bit ahead. Micro Basic Plus has a number of functions, but as far as math goes, really it's just absolute value and sign. You can peek and poke with Dendai Tiny Basic. You get absolute value. You can also do modulo remainder, so that's pretty cool. You do have a character output, and both 6800 Tiny Basic and Dendai can call a machine language program and pass arguments. The next thing to do was to put these languages through their paces, and what better paces than the original paces? We're going to go back to Kilobaud Magazine, June 1977, where Tom Rugg and Phil Feldman gave us the classic Rugg-Feldman benchmarks. I'm going to run these on my homemade 6802 monster computer running at a megahertz, and here are the results of the tests that I made. While not incredibly accurate, this is certainly scientific. We're going to take three measurements, get an average, and we'll have a rough time that it takes for each basic to run a benchmark. 7 benchmarks in total, 3 basics, so we'll have 21 tests that we're going to do. Here we have benchmark number 1. as Rugg and Feldman prescribed way back in 1977. I've added the print S and print E to help me with the timing. So as soon as I see the S, and I click the little button with my left finger right there, the program's going to run a quick loop, do no calculations for 1,000 iterations. It'll print the letter E, at which time I'm going to tap with my right finger to shut the stopwatch off, and we'll get a time. Wouldn't hurt to turn that back on so that you can see what's going on. All right, as soon as we see S, I'll tap with my left. And we're counting. Right finger ready to go as soon as I see the E. 8.24 seconds. So I'll record that. And we'll go again. Reset the clock. The big idea is that when we run this on the different basics, we'll get a comparison. As long as my methodology stays the same, start with the left, end with the right finger, and I should get, if not incredibly accurate numbers, I'm going to get relatively accurate numbers between the three basics. Now, first off, it is not fair to put some of these benchmarks on Pittman's 6800 Tiny Basic because it doesn't have 4 next loops. There's no array. You can kind of simulate it if you want with peeking and poking into memory to have an array, but it's just not fair. And with TSC MicroBasic Plus, you see that the binary coded decimal arithmetic really hampers this thing. Dendai is many times superior in terms of execution. Looking at something that all 3 of the languages could do that was stressful would have been benchmark 5. An if-then loop 1,000 times around with 4 constants doing a calculation and with a little go sub in there. MicroBasic Plus, a little faster than Pittman's, by 20 seconds, so quite a bit. But Dendai could run the same benchmark in about 17.5 seconds. I mean, that is quite significant. I wanted a more robust test for these languages, so poking around one of my favorite places to go, Rosetta Code, I found the Sierpinski carpet, and this looked like just the thing. This rather studious-looking fellow and quite brilliant mathematician is Václav Sierpinski. He lived in the late 19th and early 20th century, and the Sierpinski carpet that he came up with is a plane fractal, and it's a generalization of a Cantor set. Now, you want to ask me what those things are? Well, I don't have a math degree. Look it up. But Wikipedia tells us that this is a technique of subdividing a shape into smaller copies of itself, removing 1 or more copies and continuing recursively so that can be extended to other shapes. This looked like a great test to see how fast a language could print this thing out. And it makes a pretty pattern. And we're off. On the left, Dendai. In the middle, MicroBasic Plus. On the right, Pittman's 6800 Tiny Basic. Already, I think we can see where this race is going to end up with 1, 2, and 3. So let's move ahead in our coverage as we get to the end and see the final times. And there you have it. A clear winner, Dendai Tiny Basic at 73 seconds, followed by MicroBasic Plus at an even 3 minutes, 180 seconds, and Pittman's 6800 Tiny Basic, 234 seconds. And of course, Dendai Tiny Basic can play all the usual games. Here's Wipeout with some graphical dice. And, of course, it can play a baseball game for you. And it wouldn't be worth its salt if it couldn't play Tiny Trek. There are a couple of problems that I ran into with Dendai Tiny Basic. Number 1 being the random function. I could not get the darn thing to work. Should be pretty obvious how it would work. You have a number that you pass from the function, and you do division, and whatever is the modulo remainder, that's your number. When you divide it against the random number seed. But it just won't work. Can't figure it out. Maybe you can. Source code is available, and you can have at it. But in the meantime, I rewrote the random routine, stuck it in the very low end of memory, actually in memory location number 4 in zero page, and you can just call that as a user function, and it works the same way. Would be nice to have it work the right way, though. The other thing is, it can sometimes take an abysmally long time to load anything in here via a serial text transfer. Line delays of, say, upwards to half a second, sometimes a full second, just wasn't going to cut it. So, as much as I like the language, I want to keep using it, so I wrote a little loader program. And this will accommodate a user program that is up to 14.5K long, at least on my system, and works just fine. Character delay of 10 milliseconds and a line delay of 100, and you're in business. Dendai Tiny Basic proved to be quite popular, but as we've just discussed, there were a few little shortcomings and some things that could have been made a little better, a little faster. And there was a grad student at Osaka Prefectural University named Haruo Yamashita, and he and some buddies that were engineering students, they built a computer. They were using Southwest Technical Products 4K Basic, which was great for calculating stuff, but incredibly slow and didn't play games very well. So they wanted to take Dendai up to the next level. And they came up with Nakamozu Tiny Basic, NTB for short. Once I had read through Yamashita's website and saw that he had the source code and various other documents for Nakamozu Tiny Basic, I saw that there was going to be some work to do. Check out these addresses. That's some kind of custom graphics card right there. And as you can see, most of the comments are in a mix. It's 50-50. There's some Japanese, there's some English. The English starts going away pretty darn quickly. But thankfully, he had used some really great labeling. In addition to the labeling and what little Japanese I know and the blessed wonderfulness that is Google Translate, I was able to get a sense of what was going on here. The next thing I grabbed was the hexadecimal dump list from ASCII magazine, which Yamashita also had on his website. And the best part about this, besides having the actual bytes right there, is we have checksums. Now, the highlighting here is a little screwed up, but maybe I can grab one. You see, there's a checksum for this block of code from 0280 to 02FF. And writing a small machine language program to calculate the checksums, basically add up all the bytes and see what you get. I was able to enter this in over the course of a couple of days, check my work block by block, and come up with a byte-accurate binary. Getting that byte-perfect binary image was no small feat. I OCR'd the dump list, and then I fed it into a spreadsheet, getting a bunch of stuff like this. And you can imagine, it gets even weirder as we go along here. Check that out. And there's just stuff. There's, I think, one of the checksums right there. And there's some overlapping code here. This is address 0528, and over here on the same line is 06E8. So we had to do some separation, and I came up with a file then that looked like this. So there's block at a time, and as they failed with my little checksum calculator, I went back and poured over the code. Zeros are 8s, and zeros become C's, and all kinds of crazy things happen. 4s become A's. vice versa. But ultimately, I got all the checksums passed, and we had proper code. Then this was just simply saved as a straight-up text file, and it was pretty easy enough to dump this into HXD and then save it as an S record. From there, it was off to the F9 disassembler, where we got some nice raw output with some just very generic labels and constants and almost impossible to follow, right? So I grabbed my copy of the source code and armed with that, a section at a time, and I was doing it pretty much one page at a time, and that was enough, and replaced all of those labels with the actual labels and added comments as best I could as well. Although someone who actually speaks and reads Japanese, reads kanji, really does need to go through this. And ultimately, what I ended up with was a machine compilable source code with English comments. Well, you know, very, very badly translated from Japanese English comments. But it should be enough to get anybody on the track, going where they need to go to make this work on their 6800 system. With the original Nakamozu ready to go, all I had to do was patch it for my system, which was the expected thing you did in the 70s. Here we've got some SWAT bug equates and where my ACIA chip just happens to reside in memory. And we're going to do a little, just a little customization. About is now backspace. A quick little fix for carriage return and line feed at the end of lines. I think this had something to do with the way his graphics card worked, and with TTY output, it just wasn't quite right. So we did a little fix there. Some more SWAT bug stuff. Changing a break routine from PIA based down to a new break that uses the ACIA. Finally, there was a custom ROM called an initialized the graphics board. We don't need that, so I just knocked that jump right out of there, and it gets ignored. And finally, we patch in the address to send back to SWATbug if we type the command exit. This next chart shows just how much more feature-packed NTB is over Dendai Tiny Basic. Not so much in terms of commands. You do have cassette load and save. You can append, which is loading without clearing out memory. And you can also delete some lines right there. It's down in the functions area that you really see a big difference. But there's also some really good statement operational stuff here. The main ones, do until looping. And you have data and restore. And the asterisk is only there. It's not to say that there's something weird about it. The asterisk is the data statement. I'm not entirely sure how it works. I went through the source code because I typed it all in and went through all the comments. But yeah, that's simply how it works. And just like Dendai, you use the pound symbol for poking and peeking. Now, the myriad of functions that Nakamozu Basic allows you are really fantastic. You've got logical bitwise operators here. Read that goes along with data and restore, of course. GetString works like GetKey in Commodore 3.5 Basic. That's used on the Plus 4 and the Commodore 16, where you just wait for the input of a character. Key has been rewritten by yours truly to act way more like Commodore version 2 get statement. So that works like on the VIC-20 and the Commodore 64. You have a print using formatting function that you can use to set up tables and make things look nice. And these last two are kind of interesting. Hexadecimal 4 and hexadecimal 2. You can print out any expression or any number that you want in hexadecimal format. Pretty darn handy. There are some Nakamozu basic commands that are not included on the chart here, and they are the graphics commands. And the reason I didn't bother to include them is because while they're there, they're going to crash your system because they were written specifically for Yamashita's video board, a TVD02. I don't even know who made it, but that's the board he used. And in those days, users were expected to patch in their own I/O routines or fix up stuff for their graphics cards, addressing or modify commands, whatever the thing might need. It was available to do because people gave away their source code in those days. Once again, running the Rugg-Feldman benchmarks on the Monster 68 computer, it is quite clear that NTB is 25 to 30% faster than Dendai. And that was the whole point of Yamashita's designing the thing. He wanted it to be the fastest Tiny Basic out there anywhere. And he succeeded quite clearly. Some of them are kind of close. Here it's a second and a half on benchmark 2, less than 2 seconds on benchmark 5. But here, benchmark 7, where we've got benchmark 6 plus array assignment, we're talking almost 20 seconds difference. It's quite a bit. I also ran a couple of other benchmarks, including the Sierpinski carpet and the sieve of Eratosthenes. I practiced saying that, by the way. Huge difference in time right there. The carpet, 8 seconds. If I'd optimized the code for Nakamozu Basic, using a do until loop, could have shaved off another 4 or 5 seconds of that. But this thing flies. And just like Dendai, Nakamozu Tiny Basic can play all the games, pretty much anything you can come up with. Here we are running Wipeout. Next up, Aruba baseball dice. Yeah, we'll take a look at the instructions, why not? Now notice I'm just tapping a key when it asks me to press a key or yes or no to move on. So there's your get key string in action. Now we get to show off some of the string handling capability of Nakamozu Basic. Let's take the caps lock key off and say the name of the visiting team is the... Yep, that's correct. All right. What's the name of the home team? The Superbas. Sure. Press any key to roll the dice. Pop up on the infield. Wonder what the cat wants. And as you might recall, Aruba baseball dice is essentially a dice roller, and it tells you and interprets the dice roll so that you can keep track on paper of what's going on with the game. This is the only baseball game I currently have running on NTB. That's 3 outs. The sides are tired. The Superbas are now up to bat. So there's the home team's name coming right up. So there's a lot of possibilities here with string usage. Here's the part of Aruba baseball dice that demonstrates how strings can be manufactured and manipulated in Nakamozu Tiny Basic. Right here, we're going to get the name of the visiting team, and this will get input inside of a do loop. What we're going to do is we're going to get a character from the keyboard and dump it into an array. So array number 1 will have, or indexed variable number 1, will have those strings of characters, of ASCII characters. the arrays are dimensioned up here, where we set the start of array number 0, which we're going to need for other purposes, but the slash there, backslash, is a system variable that tells you where the end of the user program is, so we're just going to add 1 to that. And this is going to be the array for our visiting team. We're going to set it up 5 elements beyond that, 2 memory spaces per element, and we'll give, looks like 70 spaces for that, so 35 characters will be able to be put into the string. And array number 2 is open-ended. We're not defining a third one, so it just goes till you run out of RAM. So again, we set up our do loop right here. We took in a string of characters until we hit a carriage return, and we give our user a chance to say if that's correct or not, capital Y or a lowercase y perhaps. And we do the same thing here with our second array of ASCII characters for the home team. To print them out, all we have to do is come down here and we will find a couple little subroutines. We're going to print out the first array for the visiting team, and we'll do that until we hit the carriage return. And if it is, we don't want to print the carriage return, so we'll just return. And we'll do the same thing here for the home team.
And of course, Lee Chen Wang's Tiny Trek.
Thanks for watching. I know this kind of got to be a long video for me anyway, but really wanted to show you guys these 2 fantastic Tiny Basics from Japan in the 1970s. The source code and some object code as well. If you built a Hassler's Monster 68 or something similar, should work just okay. You can put it all together yourself. There's lots of programs and other things that you can do. They're located in the links in the description below, all the usual stuff. So hope you liked the video. If you did, you can like it. You could subscribe if you want to see some more content coming up here later this summer. That would be pretty cool. I would appreciate it. But in the meantime, you take care.